We now officially begin chapter 4. The book titles this Applications of Derivatives, although I really feel those applications start back with related rates in 3.9. But anyway, let's get into it. 4.1 is maximum and minimum values. So again, a different application than the previous two we've seen. What we're going to begin here in 4.1 is going to finish in 4.3. So we're going to do 4.1 and then we immediately do 4.3 because those flow together perfectly. We'll come back and do 4.2 after that because it takes a different angle. So what is this maximum and minimum values? Okay, so the idea is we're thinking about a graph. What we're going to develop in 4.1 and 4.3, we're going to develop a way to know a lot about a function's graph with only seeing the function itself, like the expression for the function. We can learn a ton about the graph of a function just based on just using calculus on the function itself. Okay, so where are we going to begin? Well, maximums and minimums. Okay, so we're going to define two types of maximums and minimums. So you see the first one here, it's called the absolute max and the absolute min. The absolute max and the absolute min are the highest and the lowest y value on the entire function f of x. Makes sense? What's the very highest y value on the function? We'll call that the absolute max. What's the very lowest y value on the function? We'll call that the absolute min. But there is another type of max and min. We call it the local, or sometimes you hear the word relative max and min. Truth is, we spend a lot more time looking at local maxes and mins than we do absolute. So let's read that definition. The local, we're just going to call it the local, but you will hear it maybe in other books, or other teachers might call it the relative. What is a local max or min? It's the highest or lowest point in a small neighborhood of f of x. So it might not be, say, like a local max, it might not be the highest point on the entire function, but it's the highest point in a small area, or we use the word neighborhood, or a local min. It might not be the lowest y value on the entire thing, but it's the lowest y value compared to the ones around it in its neighborhood, if you will. Okay, so let's just put down a graph and just see if we can identify absolute max and min, local max and min, and then there's going to be some nuances that come out of this as well that are going to be really helpful to see here. So I'm just going to start off with this graph right there, and I've labeled 4 points there. So it begins at 2, 3, curves up to 3, 7, drops back down to the point 5, 1, and then back up again to 8, 4, and then it drops off down and continues down to negative infinity, like so. So maybe take a moment, sketch that. You know, it's this nice smooth graph. Okay. So let's start with the absolute max. What is the absolute max of that function? Well, what was the definition again? It's the highest y value on the entire function. Well, the highest y value, of course, is the 7. So the absolute max here is 7. What about the absolute min? Now this is tricky. The absolute min is the lowest y value. But as you see, you're like, okay, you know, like there's a low y value, but over here there's y values that are lower than 1. So these y values are all less than that y value. Then you think, okay, but then if this goes down, 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 there is no lowest y value, right? Because for any y value you find, there's some that are lower because that thing just drops off. So here, and this takes a second to wrap your head around, there is no lowest y value. There is no absolute min. So let me show you. Got it right there. The absolute max, of course, was the 7, the highest y value, but there is no lowest because the way this thing falls off. So we just say none. There is no absolute min. Okay. How about the local maxes and the local mins? Let's start with local maxes. So a local max is the highest point in a small neighborhood. So you think, all right, the highest point. Well, this point here, it's the highest. And if you think of its neighborhood, you could like draw like a small circle. Like, truth is, it's the highest one on the entire thing. But if you just think of its neighborhood, it's the highest of the points that it's nearby. The same is true here at 8,4. That's a local max because it's the highest point of all the points that is nearby. It's the highest one. So both 3,7 and 8,4 are local maxes. Okay. How about the local mins? 5,1 is a local min. It's the smallest point, or the lowest point in its neighborhood. And you might be tempted to say 2,3 is a local min as well, but we're not going to consider that a local min, and that's kind of one of the other nuances here. So let me show you my answers for the local maxes and mins. 3,7 and 8,4. Only one local min at 5,1. Now, before we get to the 2,3, I actually want to point something else out. Notice that the absolute maxes and mins, the absolute, they're only the y value. So the absolute max is 7, the highest y value. The local maxes are the entire point. We put 3,7, 8,4. So that's a little nuanced difference, right? Absolutes are, we're just talking about y values. It's like we don't care where it occurs. Just what is the highest of all the whole function? What's the highest it gets up to? We don't care where. But the local maxes, we do care. It's at 3,7. It's at 8,4. Like, where does that neighborhood occur? And then at 5,1, where does that neighborhood occur? Don't just tell me 1. I want to know the 5 also. All right. Okay, now finally, what's up with the 2,3? Why don't we include that in the local mins? Because we don't allow for endpoints to be local maxes and mins. So I've got this note down here at the bottom. Endpoints. They can be absolute maxes and mins. An absolute max or min could happen at an endpoint if it happened to be the highest or the lowest, but they are never local maxes and mins. We never consider an endpoint, and that's just something, there's not really a great reason behind it. It's just, that's just how we think of it, and there is a good reason. It's not clear in the definition. There is a good reason behind it, and it has to do with calculus and derivatives, which we're going to get to in a moment. But just maybe keep that in mind. Absolute maxes and mins, it's only the y value, and it could be an endpoint. If that was like the local min, or sorry, the absolute min, and it just went up from here, let's say, then that's a possibility. But we never consider an endpoint to be a local. Maybe one way to think of it is, if you were to think of a neighborhood, it only has neighbors on one side. Not on two sides. Maybe that's kind of a justification there. Okay. I think we probably got a good handle on this as we go forward. I want to just real quick, I hinted at this a moment ago, where this is going. So there's these two types, and we look at them separately. So some questions, they're going to be all about the absolutes. Other questions are going to be all about the local. We don't mix the two. So we're either looking for absolutes or we're looking for locals. We're never looking for both. We're going to spend a lot more energy on the locals than we are the absolutes. The absolutes we definitely give time to, but we spend a lot more. And we're going to begin our discussion focused on the locals. So, just give you an idea where this is going. All right. Starting right now. We want to develop a way to identify where the local maxes and mins occur. If we can identify where the local maxes and mins occur, that gives us a huge insight into what the graph of a function is doing, even if all we can see is the expression for the function. Okay, so here's a theorem. It's Fermat's theorem. If you've ever heard of Fermat, he's infamous for what's called Fermat's last theorem. This is not that. Fermat's last theorem has nothing to do with calculus. Really interesting, got an interesting history. Some documentaries came out about it a few years back. A really good book called Fermat's Enigma. Very readable. It's not, super heavy like textbook. Anyway, okay, Fermat, pretty interesting guy. And along the way, he developed this theorem. I think it's his only contribution to calculus. Says if f of x has a local max or local min at C, then one of two possibilities. Either f prime of C equals 0, or f prime of C does not exist. Okay, so this is kind of like another one of those theorems where you're like, oh, I wish I could have lived back in those days, because I could have said that. Like that's nothing like really earth-shattering at all. But let's explore a little bit with some pictures. Okay, so we're saying if there's a local max or a local min, then either the derivative there is 0 or the derivative there does not exist. So I'm going to bring back the previous sketch, not labeling the points this time, just kind of sketching it out. Graph kind of looked a little something like this. Okay. And we had realized, hey, there's a local max here, and there's a local max here, and there's a local min here. So it turns out, and we're just going to call each of those C, because they're saying if there's a maximum at C, okay, so that's a C, or maybe you call it like C1, C2, C3, whatever. Is what he's saying, would that follow? Is either the derivative at those C 0 or not exist? Here, in this picture, the derivatives at each of these locations equal 0. Because you think if you were to draw a tangent line, wouldn't that tangent line at a max, isn't it horizontal? If you're really at a maximum, both the maximums have a horizontal tangent line. The minimum has a horizontal tangent line. The slopes of those tangent lines are all 0. So at each of these locations, f prime c equals 0. Yeah, that seems so natural, right? If you're at a maximum, you're like peaked on that curve, so you get a horizontal tangent line. Or if you're at a minimum, you bottomed out, and it's a horizontal tangent line there too. So that explains this one. That one's pretty intuitive. This one's a little bit tricky though. F prime c does not exist. Let's see an example like that. When would f prime c not exist? Well, here's a drawing. Let's just go ahead and scroll that up. That'll work. What if you had something that wasn't so smooth and rounded, right? What if you had this sharp corner, or technically we call it a cusp, right? So this would be like a piecewise function. You got this line coming up there, and then this other line coming down. They meet there. So it is continuous, but it's not differentiable because of the cusp. Well, if you think about it, this is a local max. I mean, it's the biggest point in its neighborhood. I mean, truth is, here it's an absolute max, but okay, well, we don't have to go there. It's a local max, but there's no tangent line there. The derivative does not exist due to the cusp. So it's possible to have a local max or a local min, at a cusp, and in that case, the derivative would not exist. So there's the only possibilities. Either this is the way you get a local max or min, or this is the way you get a local max or min. That's it. Before we conclude this video, and then we'll get to examples, I need to point out one interesting case. And that's my last drawing down here. Okay, let me explain. So what I've drawn here is x to the third. This is a good, we'll get something specific here. So not just kind of a random drawing of a function general, but we're specifically y equals x to the third, so we can really see it. Okay, so it's got this kind of cubic shape that we're familiar with. Okay, the point of interest is at the origin. So you think, hey, what's going on with the derivative at the origin? You think, well, I'm not really sure. So let's see. For y equals x to the third, y prime equals 3x squared. So what is the derivative doing there at 0, at x equals 0? Well, at x equals 0, you plug that into your derivative, you get 0, right? Right there, you have a horizontal tangent line. And maybe that is interesting to some people. Maybe it's not all that surprising to a lot of you. Okay, so the tangent lines here are positive, then they start to level out, and right there at the origin, the tangent line actually goes perfectly flat, perfectly horizontal, but then it starts to go positive and more positive again. Okay. You think, okay, big deal. So what? You got a horizontal tangent line there. The derivative there equals 0. However, the point 0, 0 is not a local max or a min. Okay, that's not a max or min, right? Yet, the tangent line is horizontal. So, when you look at Fermat's theorem, what he's saying is true, but don't take it too far. If there's a local max or a min, then one of these has to be true. However, these could also be true, either one of them, and it not be a local max or min, right? So just because the derivative is 0 doesn't mean that's a local max or a local min. Same could be true of a cusp, right? You could have a cusp. I didn't draw a picture of one, but maybe just like a quick sketch. Like you could have a cusp and it not be a max or a min, right? So the derivative does not exist there, but that's not a max or a min for sure. So these things can happen without producing these. But if you really are a max or min, one of these is going to occur. Okay, so what the takeaway from this is, we know that local maxes or mins have to fit this, but where these things occur, those might include other points that we're not gonna don't actually end up being local maxes or mins. Okay, so we're gonna develop this thinking further in 4.3. Let's stop this video here. We'll get to some examples here in a moment.